Hey guys, so in this video we're going to talk about the Kutta Joukowski theorem and how it can be applied to a finite wing. So hopefully this video will help you do the homework related to this section as well. Okay, so moving along, well, we saw in class that lift equals rho v gamma, right? And we derived this expression. So now let's apply this to the airfoil. So as the first thing that we need to do is look into what is called Kelvin's theorem. The Kelvin theorem states that the total change or net change in circulation as a function of time should be zero. Okay, so what this means is that the circulation should be constant. Right, here is an example of jet being ejected out of a nozzle. Right, these different figures shows the jet output at different convective or different times. Okay, so now if these are again vorticity plots, right? Now if I integrate the vorticity in this given area as a function of time, what I will actually see is that it will be constant. In fact, the red zone and the blue zone cancel each other, and you may even get zero. Okay, but the point is, it's not the Kelvin's theorem doesn't say circulation should be zero. It just says the circulation should be constant, which means circulation cannot be generated or cannot be removed from a flow field. Okay, that's Kelvin's theorem. So we're applying Kelvin's circulation theorem to the airfoil. So whenever you have a airfoil which is starting its motion from a stop position, this is what happens. Here is a numerical simulation. So what it happens is that when an airfoil moves through air, when it starts, it creates what is called startup vortex. Okay. Now, if we want to apply Kelvin's theorem, let's take a control volume around this area, around the airfoil. So we have the startup vortex in here. Now, Kelvin theorem states that there should not be any generation or change in circulation. So that means if the startup vortex is forming with the given circulation, there needs to be an equal and opposite vortex forming somewhere in the control volume that will make the net circulation change zero. Okay, and guess what? That circulation is basically what we call like bound circulation, or what is called bound vortex. So it's sort of like an imaginary vortex that we assume that is on the airfoil, which is equivalent and opposite to the strength of the startup vortex. So, as we talked about in class, an easiest way to kind of relate this concept of bound vortex to the airfoil is by considering just a point vortex, as is shown in this figure. Right, let's consider a vortex, and let's say that at some point the velocity from a certain radius is v, and then at the same radius on the other side is negative v because spinning in the opposite direction. Okay, now imagine you have a free stream velocity impinging this vortex. Okay, now think about what would be the actual velocity at these two locations. It's only safe to assume that, well, it's only intuitively we can make this assumption that the velocity on top will be u infinity plus v, and the velocity at the bottom vortex will be u infinity minus v, right? Now, to connect this back to the airfoil, if we assume an actual airfoil there, and think about what's actually happening on top and bottom of the airfoil, at top of the airfoil or the upper surface, you have a higher velocity, and at the bottom, you have a lower velocity, right? This is analogous to how an airfoil generates lift, correct? So when there's high velocity, you have low static pressure, and when there's low velocity, you have high static pressure, and the difference in pressure acting on the correlate would lead to lift, right? That's the whole idea behind this bound vortex. So in other words, this velocity difference can be thought of as it's been created by what is called bound vortex. The strength of the bound vortex sort of influences how much lift the airfoil is producing. Okay, that's how we can connect the concept of bound vortex, the Kutta Joukowski theorem, using the Kelvin's theorem. Okay, now we still have to connect this to a finite wing, right? So before we move on to that, let's look at the different types of vortex that exist in 2D space. In 2D, you have a point vortex. For example, the bound vortex that we talked about in the last slide, that's an example of a 2D vortex. But if you actually look at a 3D space, if you stretch out that point, you will actually get a vortex line, right? That's shown in this area right here. And it's also possible to have a vortex tube. And vortex tube is nothing but a bunch of vortex lines joined together to form a tube with a constant circulation. Okay. Now, in order to connect the Kelvin's theorem, Kutta Joukowski theorem, and the bound vortex to an actual finite wing, we need to make use of these Helmholtz theorems. Okay, so Helmholtz postulated 3 different theorems. The first one is the strength of the vortex tube or vortex line defined by circulation across any cross-section of the tube is constant. Mathematically, what this amounts to is that the circulation or vorticity cannot be generated. So if you think about conservation of mass, you have the same divergence, del dot V is 0, but in this case, it's del dot vorticity is 0. All that means is that there's no divergence, which means there's no magic appearance of vorticity in the flow field anywhere, or disappearance for that matter. The second theorem states that the vortex lines cannot end in a fluid, and vortex lines on tubes must appear in closed loops, extend to infinity, or start or end at solid boundaries. What that means is that, again, it's obvious that it cannot end anywhere, basically the vortex lines, and the tube must be in closed loop, extend to infinity, or start and end at solid boundaries. Okay. So the third theorem states that in a barotropic and constant pressure inviscid fluid that is initially irrotational will remain irrotational, and fluid does not and cannot create vorticity. This sort of ties back to the first theorem of Helmholtz, which states that vorticity cannot magically appear. So that's true with the third theorem too, is that an irrotational flow will always remain irrotational throughout. Okay, if providing the assumptions hold, which is barotropic and inviscid. Okay, now you may think, okay, these are all just made up theorems, and if there is, you may think whether or not there is any validity to these. Helmholtz vortex or vortices can actually be found in nature. Here is an example of beluga whale actually playing with its vortex ring that actually forms through its nodes. These vortex ring is a perfect example of Helmholtz theorem, especially theorem number 2, which says a vortex ring or a tube cannot end in a fluid. It has to form a closed loop, and that's exactly what it does. Right. And if you go to YouTube, you'll find a lot of vortex cannons, which generates vortices, which is, it's an example of Helmholtz vortex. And these vortex rings is a very interesting phenomenon. Smarter Every Day, one of the YouTube channel, has a very good video on the vortex impingement. I would recommend you guys going and watching that. But basically what this says is that the rotation of the fluid in the circular area with the moving, it's moving at a constant speed. So as we talked about in class, this leads to what is called a total pressure change from Procos theorem, right? So some of these Helmholtz vortices does exist in real life, and if you want to know more about vortices, I encourage watching this video as well, which is Secret Life of Vortices, Evolution and Destruction. Okay, here's another example of a vortex tube actually ending on a solid boundary, which is the ground. I believe this is a C5 Galaxy cargo airplane, and these engines, when they spool at high speeds, it causes the air in front of the engine to swirl. And what you are seeing here is the condensed vortex core. The reason why you are able to see the vortex core is because the pressure is so low that it actually knocks off the water molecules in air. That's sort of what you're seeing as a white streak. Okay, again, so another example. All right, now we just want to make sure that we can determine lift from a finite wing using Kutta Joukowski theorem, right? By connecting what we call the Kelvin's theorem, the Kutta Joukowski theorem, the bound vortex, and also the Helmholtz theorem. Okay. Now, if you look at a flow around a finite wing, you have what are these called vortices, right? Now, if you assume there is a bound vortex along this wing right here, okay. Now, Kelvin said that, or Helmholtz said that vortex cannot actually end. Vortex line cannot end in a plane or in the ground. So what we do is we can think of the same thing, but we can extend this vortex line or this bound vortex line to infinity. Okay, and you can do the same on the other side too. Now, if you look at a flow around a wingtip, there is already a spinning vortex that forms as a result of, well, pressure difference between the upper and lower surface, right? So this is where the concept of bound vortex meets the reality, because we've been assuming this bound vortex is an imaginary thing, right? And of course it is an imaginary thing, but using Helmholtz theorem, we can connect it to something very real, which are wingtip vortices. And if you look at many pictures of airplanes, these wingtip vortices are circulating regions of air which has a strength associated to it. And that strength is often related to the lift created by the airplane itself, right? Because the more pressure difference that occurs between the top and bottom surface of the airfoil, the more lift it produces, and that translates to more or higher strength wingtip vortex. So hope that makes sense. Now is where we use the Kutta Joukowski theorem to find the vorticity in the wingtip vortex, therefore circulation, plug it in the Kutta Joukowski theorem, and actually get lift out of it, right? And one small change that we need to make sure in this case is that since we're looking at finite wing, we need to add this b, which is the span of the wing, in the equation, so that you will actually get the net lift across counting for the span. Okay. One of the very important or interesting things about this equation is that these wingtip vortices tell us most of the story about what's going on the wing, on the airplane itself, because the strength of the vortices, if you think about it, depends on the angle of attack, because if you change the angle of attack, you increase the strength of the vortex, you increase lift, right? You increase lift and then increase the strength of the vortex. But it can also be thought of in relation to the weight of the airplane itself. If your airplane is heavier, you're bound to create more lift to lift that weight off the ground, and henceforth your vorticity, or in your circulation in your wingtip vortex, will also be greater. Okay, that's one of the reasons why a small airplane cannot, take off within very close distances from behind a bigger airplane, right? A Cessna cannot take off behind an A380, otherwise, well, it'll fall off the sky. Okay, and usually the wait times between two airplanes to take off depends on how fast these vortices dissipate. So if you're taking off behind a bigger airplane, you have to wait longer than you would wait for a smaller airplane. Okay, so that's the beauty of this equation, is that it takes a concept which is purely theoretical, and to be honest, this bound vortex, people have either pieced things together to make sense of the world back like 200 years ago, and they connected this concept to something you see in real life, which to me is pretty amazing, right? So how can you use this information to actually calculate lift from wingtip vortex? Okay, now about a couple of years ago, or I think was in my PhD, what I did is I looked at the wingtip vortex of a CLARKY airfoil, or CLARKY wing. It's an aspect ratio 6 wing, if you could see in this image, right? I looked at the wingtip vortex to understand what's going on. Like, we did a study on how wingtip vortex interacts with the free shell layer, but anyway, we have the data, we collected the data using what is called particle image velocimetry. Okay, that will allow us to see the roll-up of the wingtip vortex. Now, if you look at this test setup, I'm only allowing one side or one wingtip to be in the flow. Okay. Now, I mentioned that this is an aspect ratio 6, but in fact, if you look at the dimensions, 38.1 centimeters span and a 12.7 centimeter chord, what you actually see here is the span is about 3 times long as the chord, right? So that actually gives you aspect ratio 3 and not aspect ratio 6. The reason why I say aspect ratio 6 is because it's a semi-span aspect ratio 3 model, which means that by blocking one end of the wingtip or one end of the wing, this splitter plate, as we call it, acts as a fuselage. Okay, so that means only one side of the wingtip is actually exposed, allowing only roll up of one side of the wingtip vortex. Okay, and you can actually see that in here. So there is a concept called method of mirror images, and what that allows you to do is, using simple math, we can claim symmetry, which means that whatever field that you observe in here or before the splitter plate is the exact same field that you observe on the other side. Okay, and because of that, when you look at a flow field, because you're blocking one end of the splitter plate, one end of one wingtip, the flow field will actually resemble an aspect ratio 6 and not aspect ratio 3, because you're cutting out one side of the wingtip vortex influence that will change the way the flow goes around the wing, and the way the flow goes around this wing will resemble an aspect ratio 6 flow field and not aspect ratio 3. Okay, so that's why you see these. That's why I said it's an aspect ratio 6, even though it's an aspect ratio 3 actual wing. Okay, now using the data, you can see this vortices. Again, I created these using streamline command. Okay, this is the data that you will be given. So in this homework, I'll give you the vorticity, or not vorticity, you'll be calculating vorticity, but I'll give you the velocity data, the U and V velocity data for 2 degree, 4 degree, 6 degree, and 8 degrees. Okay, these videos sort of can tell you a story about how these wingtip vortices are, forming and evolving at different angles of attack. At 2 degrees, you may see the wingtip vortex is not fully formed, right? At 4 degrees, it's sort of, it's kind of getting to this full circular shape. And by the time you go up to high angle of attack, you see this clear rotation of the wingtip vortex, right? So this is, again, pretty interesting. This is what you'll be having. So you have data set of X, Y, U, V for all these different cases, and you'll be finding vorticity and circulation. Okay, here are some of the useful MATLAB codes that will help you do this. I uploaded this homework, uploaded this data set in Isidore. Okay, so please go and download. When you load this MATLAB file, you will get different angles of attack. Okay, alpha 2, alpha 4, alpha 5, alpha 6, and alpha 8. And you will see that it has 4 different columns. The first column is X, second column is Y, third column is U, and fourth column is V. Okay, and this was taken by a PCO 1600 camera, and our post-processing algorithm resulted in a matrix of 99 cross 74. So as we talked about in class, what this means is that I have 99 rows and 74 columns. Okay, so that's my image, that's my matrix right there. So when you use this reshape command, you will reshape a column into a grid. Okay, so note that this is a different matrix from last time. Last time when we looked at the plunging plate data, the matrix was 126 cross 126. Okay, you will also be using a trapezoidal command, which allows you to perform numerical integration in 1 or 2 dimensions. Remember, vorticity or circulation is a area integral of vorticity and area integral, right? You need to be able to perform area integral in MATLAB. Okay. Now, if you want to look at this slide, I would recommend pausing this, because in this slide, what I did is I compared the validity of the numerical method using trapezoidal command and the analytical method. Okay. What I did here is that the analytical method, now I take this function, right? If I use the analytical method to integrate and find an answer, it's the same answer, well, pretty close as to find it numerically. Okay, so this method of numerically performing area integral is valid, right? So this is the vorticity that you should be getting when you actually plot or calculate vorticity in your data. Okay, 2, 4, and 6 degree. There's a 5 degrees in there as well, which you can plot. But what this shows here is that as the angle of attack is increased, you can see that the vortex radius is actually increased. But more importantly, look at the vorticity, right? It's darker in the center. The darker represents a concentrated vorticity, concentrated magnitude of vorticity. The negative, it just indicates the sign, okay? It just indicates the direction of rotation. So when you take, if you take this, just take one, say for example 2 degree, and if you want to find circulation, remember circulation is an area integral. So that means you need to integrate with respect to x, and then you integrate with respect to y. So if you use this trapezoidal function, you will be able to determine a area integral of this flow field. Okay, just keep in mind that these x and y are vectors and not matrices. All right, so take the first x-axis column or row, or y-axis column or row. Make sure that you integrate with respect to x and y as vectors, with these as vectors. Okay, and when you do that, you will actually get the value of circulation. All right, so I'm going to stop the video right here, and I'll post this online for you guys to take a look. I hope this helps. Right.